Okay, so on Wednesday we started Unit 3, which is the beginning of our dosage calculation unit. And our big discussion Wednesday was about those dilutions. And the dilutions had two purposes. One was to serve as a carrier, to take a medication or some sort of active ingredient, which we referred to as just a generic term, serum, into the body. It's just a way of getting it into a patient, whether it's through an IV or an injection, rather than having to take it orally. If we had a 2 in 9 dilution, so our ratio here was 2 to 9. The 2 represented the parts of serum, and the 9 represented the parts of total solution. And remember, there were two other ratios that come from that ratio. One of them is the ratio of serum saline. Remember, NS is normal saline or neutral solution. And so we still have two parts of serum, whatever that active ingredient is. The saline makes up everything else in the total solution. So if we have 9 parts total solution and 2 of those parts are serum, 9 minus 2 gives us 7 parts of saline. So that ratio of serum to saline is 2 to 7. And the final ratio that we might be interested in is the ratio of saline to total solution. And that one we pretty much already have figured out. There are 7 parts of saline here. Again, that is from the total of 9 parts minus the 2 parts of serum out of that 9 total parts that we had. And for any given problem, one of those ratios may be more useful or more fitting than the others. Things like how much saline should be combined with 60 milliliters of serum to create or constitute a 3 in 10 dilution. So here the dilution, 3 in 10, and once again I'm going to label it. I know it gets repetitive after a while, but the 3 represents the parts of serum, and the 10 represents the total solution, total part solution. And we want to know how much saline, how much water should be combined with that 60 milliliters of serum. So what we want here is we want a relationship between the serum and the water, the saline. So we're looking for that serum to saline ratio. There's still 3 parts serum. If there's 10 total parts, minus the 3 parts that are serum, that leaves us with 7 parts saline. So this is a 3 to 7 ratio is the one we're looking at to solve this problem. And then, of course, we use that 3 to 7 ratio. The 60 milliliters is the part serum, so that goes with the 3. And then we cross multiply and divide. 7 times 60 divided by 3, excuse me, gives us 140 milliliters of our saline or sterile water to mix with that serum to make that dilution. The other thing we looked at the very end of class was diluting an existing solution. So what we were looking at up above, we were looking at a pure serum being mixed into water into our dilution. Here we're going to look at a concentrate. It's going to replace our serum. And all that is a solution with a higher concentration that we're going to be diluting to a lower concentration. So when we look at this, let's say that we have 120 milliliters of 24% solution. What dilution should be used to dilute it to, let's go to 8%. So to figure out the dilution, we need to figure out how much saline, how much sterile water needs to be added to this solution. And what we did on Wednesday was we looked at that back at that solution formula, the amount of serum is equal to the concentration. Remember, concentration is just the percent written as a rate or decimal times the total volume. So for this example here, the concentration is 24%, so that's 0.24. And the current volume, the total volume, is 120 milliliters. We multiply that out, 0.24 times 120 gives us 28.8 milliliters of serum. That is not going to change. We're not going to add any serum. We're not going to add any of our active ingredient. The only thing we're going to add here is saline or sterile water. Nothing with any medicinal properties to it. So we want to work this formula here backwards using the 8% to see what our new total volume needs to be. So the amount of serum is going to stay at 28.8 milliliters. We want to change that to 8%, 0.08, and we're going to find our new total volume. I'm just going to call that capital V for volume. And to solve this, of course, we're just going to divide by 0.08. So we take our 28.8 divided by 0.08 should give us, I believe, 360. There it is. 360 milliliters is our new total volume. So then we need to figure out a dilution. Our dilution, well, we had 120 milliliters of the 24% solution. We now need to change the total volume to 360 milliliters. And that what's going to be added, of course, is just that inactive material or normal saline or sterile water. So what we have here, the 120 milliliters of the 24%, that is our concentrate, or what's going to be used as our serum. So 120 milliliters of that 24%. And this is the total volume, not the amount of water added, it's total volume. 360 milliliters. And we reduce that ratio. The milliliters cancel out, same units. On both 120 and 360 can actually be divided by 120. Give us 1 to 3. So this is a 1 in 3 dilution. Now that means for every 1 part of the 24% serum, we're going to end up with 3 parts of total solution, which means it's 1 part of the 24% to every 2 parts of sterile water, neutral solution. Remember that 1 in 3 dilution is a 1:2 ratio of serum to saline. Well, if we look at the example we did Wednesday and this example here, that dilution, 1:3 here, has a very special relationship with our concentrations. A ratio of concentrations here, we ended with 8%. We started with 24%. If I reduce that ratio of percents, the percents cancel out. Both 8 and 24 actually divide by 8 and give us a 1:3 ratio. That ratio of ending concentration to starting concentration is the same as the dilution we need to perform to reduce that concentration. Or if we know the dilution, it'll help us then to tell us what the new concentration would be. So let's take a look at some examples there. Find the dilution necessary to reduce a 42% solution to 12%. So again, the dilution ratio, the dilution itself is going to be equal to the ratio of the concentrations. It is the ending concentration compared to the starting concentration. So our ending concentration here would be the 12%. The starting concentration would be the 42%. Now I'm entering these as percents. You could enter them as rates too, as 0.12 and 0.42. They would reduce the same. We just have to move the decimals to get the decimals out of our ratios before we reduced them. So here, the percents cancel out. Both 12 and 42 can be divided by 6. 12 divided by 6 is 2. 42 divided by 6 is 7. So that is saying that this is a 2:7 dilution. To reduce that from 42% to 12%. Similarly, we might find the new concentration. If a 36, maybe a little bit, let's go 32% solution is used in a 3:8 dilution. So now we have our dilution ratio of 3:8, and we're going to have that dilution is going to be equal to our ratio of concentrations. Well, the 32 is the starting concentration. That's going to go on bottom. We know that after the dilution, we're going to get a lower concentration. So we're going to go ahead and cross multiply and divide here. 3 times 32 divided by 8 gives us 12%. That new concentration is 12%. So as we had mentioned last class, ratios and proportions are going to be a huge part of doing our dosage calculations. This is one application of them right here. Now the next step of this, since we're going to add some sort of saline to this to reduce that concentration, would be to figure out how much saline needs to be added. So we might ask how much sterile water or normal saline should be added to 60 milliliters of 28% solution to create, let's make it 16% solution. So here we can use this process we just did to find what dilution is necessary. So we're going from 28% to 16%. So 28% is the starting solution. 16% is the ending solution, so that'll go on top. And we'll reduce that ratio. The percents cancel out. Both 16 and 28 divide by 4. 16 divided by 4 is 4. And 28 divided by 4 is 7. So this is a 4 in 7 dilution. Now remember that 4 in 7 dilution, if I write it as a ratio, the 4 represents the concentrate or serum. In this case, that is the 28% solution. And the 7 is the total solution, or the final amount. In this case, that would be the total amount of the 16% solution. We only want to know how much water do we add, how much saline do we add to it. So what we want is the ratio of serum or concentrate to water, which is normal saline. Well, if that ratio, there's still 4 parts of the concentrate, that doesn't change. If there are 7 total parts, and 4 of those parts were concentrate, 7 minus 4 is 3, there's 3 parts saline. So our ratio of concentrate to saline is 4 to 3. And now we can fill in the rest of that ratio. We started with 60 milliliters of the 28% solution, so that was the concentrate, 60 milliliters of the concentrate. We cross, multiply, and divide. 3 times 60 divided by 4 is 45 milliliters of sterile water or normal saline that should be added to that original 60 milliliters to dilute that down to 16%. Well, this process here is not terrible as far as I'm adjusting the concentration. But if we look at how that was done before we had this shortcut, let's do the same problem here of how much serum or how much saline should be added to 60 milliliters of 28% to get 16%. So what we had done before we had that shortcut of using the dilution to adjust the percent, was we went back to that solution concentration formula, where we said the amount of serum was equal to the concentration times the total amount. I'll just put concentration times total volume, so C times V. So here that was 28%, 0.28 times 60 milliliters. And so 0.28 60 is a 16.8 milliliters of whatever the serum is here. So that original 28% solution held 16.8 milliliters of that original serum. To reduce it to 16 milliliters, or 16% I should say, we're still going to have 16.8 milliliters of that serum. We just want this to go down to 16%, so 0.16. we're going to find a new total volume. So we divide by the 0.16, giving us, what is that, 105? It is 105 milliliters. That is our new volume. So then to figure out what we would add for water, it's just a matter of taking the old volume, 60 milliliters, subtracting it from the new volume of 105 milliliters to get that we would add 45 milliliters saline. Well, as we look at what we did here, we use that solution formula to find the amount of active ingredient, the amount of serum. Then we use the serum back in the solution formula to find the new volume. This number here is always going to be the same. So really, if you look at systems of equations, we can set this part of the equation equal to this part of the equation. And what it comes down to is something called our solution concentration adjustment formula. Or it could simply be put as change of concentration formula. And what it is saying is we have a starting concentration times a starting volume. Now, some textbooks say C1 times V1, others say V1 times C1. Same difference, you're going to get the same result. And then we're going to have a new concentration, we'll call that C2, times a new volume, we'll call that V2. So in this case, we had 60 milliliters of 28% solution. We wanted 16% solution. So that meant that in this formula, this will be our starting values, the 60 milliliters and the 28%. Now, one of the nice things about this formula is we don't have to put our percent into a rate or a decimal anymore. We can leave it as simply 28% if we want to. The 28% times 60, that is our starting concentration and starting volume, equals, now obviously there's going to be one value we don't know, so that'll have to be on the other side here. The new concentration, we do know that's our 16%. Since I left this as 28, I have to leave this one as 16. I don't have to turn them into decimals, just whatever I do with one, I have to do the same for all the percents in that problem. And what I'm looking for now is my new volume, V2. Now this 2 here does not affect our calculation at all. That's just saying that this volume is a different volume than that V1. So to solve this, we'll do the 28 times 60, which of course was our 1680. It was 16.8 before, 1,680 now because we left that as a percent rather than changing it into a rate, equals 16 times V2. And to solve for V2, we divide by the 16 to get rid of it. Once again, we get 105 is our new volume. Now we look at what volume the 60 was in milliliters. This volume is also in milliliters. Now this is still a volume, a total volume, to get how much of our saline should be added, we would still have to go back and subtract those volumes. So we might have something like this. Find the new concentration. If 75 milliliters of NS is combined with 125 milliliters of, let's do 40% solution. So we can go ahead and just use this concentration adjustment formula or change of concentration formula. First concentration times the first volume equals the new concentration times the new volume. So it really doesn't matter which one we put on which side. I'm going to put, we have 75 milliliters of NS, that's our water being added. We're going to put that on hold right now. We need one of the solutions that we know both the amount and the concentration, both the volume and the concentration, and that's right here. We have 125 milliliters of 40% solution. So I'll put the 40 in for the concentration. Again, I don't have to make that a decimal. If I do, then I'd make whatever I put in for this concentration, I'd also have to make a decimal. So 40 times a volume of 125 milliliters equals, now on the other side, I'm trying to find the concentration, because find the new concentration is what we're asked. But we have to be careful about the new volume. The new volume is not 75 milliliters, it is 75 milliliters plus the 125 that was already there. We added 75 milliliters of saline to that 125 milliliters of 40%. So this formula will now become, well, let's just combine what we can on either side. On the left side, we can do 40 times 125, which I believe is 5,000. Double check that. It is. On the right side, we have to combine the 75 plus 125, which is 200. Notice I can remove the parentheses now. And to solve this, it's simply going to be dividing by the 200. 5,000 divided by 200 should give us 25. And it does. So 25 equals C2. Remember, C2 is the concentration, so that is saying 25%. So if we add 75 milliliters of sterile water to that 125 milliliters of 40% solution, the new concentration is 25%. Find the new volume if, let's do 240 milliliters of 30% solution is diluted to 12%. So again, it's that C1 times V1 equals C2 times V2. Like I said, it would work out exactly the same if it was V1 times C1 equals V2 times C2. Multiplication is commutative, so it doesn't matter what order we put them in. Each textbook will give those a little bit different order. So anyway, let's plug in. We're going to use the one that we know both the volume and concentration for. That is the 240 milliliters of 30%. So put 30 in for the concentration, or 240 milliliters in for the volume. Equals, on the other side, we know the concentration. It's going to be 12% times, we're looking for that new volume. So then down here, 30 times 240 is 7,200 equals 12 times V2. And we'll divide by the 12. 7,200 divided by 12 is 600 equals V2. Now, look back to see what our volumes are in. That is milliliters. So this is 600 milliliters. That'll be of the 12% solution. we might ask, a little bit more practical side of things is how much 18% solution is needed to create 300 milliliters of 12% solution. So again, it doesn't matter which one we put where. I'm going to start out with the 18% solution. I don't know the volume. It's asking how much. So it's 18 times V1 to create 300 milliliters of 12% solution. So 12%, or just 12, goes over here, times my 300 milliliters. I'm just going to make a note that's milliliters there so I don't have to look back in the problem later. And then I'll combine what I can combine. Well, on the left side, there's nothing to combine, so that's just 18 times V1 yet. On the right side, 12 times 300 is 3,600. Then to solve for V1, we divide by 18. V1 equals 200. Our volume was in milliliters, so this is also milliliters. So what that is saying is we would start with 200 milliliters of that 18% solution in order to create 300 milliliters of that 12% solution. We might ask how much sterile water or normal saline should be added to, let's do 90 milliliters of 45% solution to create 18% solution. So let's take a peek at this problem here. We are starting out with 90 milliliters of 45%. So 45% is our concentration times 90 milliliters. We're trying to create 18% solution. We want to know that new volume. So we'll solve this. 45 times 90 4,050 equals 18 times V2, doesn't change yet. And then we'll divide by the 18. 4,050 divided by 18, I believe that's 225. It is. So 225 is our new volume. Now that's 225 milliliters because our volume was in milliliters, but that's not our answer. This is the new total volume. You have to remember what we were asked was how much saline should be added. Well, if I am going from 90 milliliters to 225 milliliters, and the only thing I am adding is sterile water or normal saline, the difference in those volumes is the amount of water that was added. So we ended up at 225 milliliters. We had started with 90 milliliters. We subtract, get a difference. Is that of 135 milliliters of saline that's going to be added. You can see we can keep going around and around in circles here on different combinations, different inputs to get different outputs of this formula. But the gist of it is just very powerful. We often need to reduce the concentration of a medication to make it either safer to administer to a patient or to allow the flow rate to be accurate. For example, for an IV infusion, many of our infusers have a limit to how slow the IV can go into the patient. Let's say that the limit on a certain infuser is that it cannot infuse no less than 5 milliliters per minute. Well, if our patient can only handle a certain amount of medication per hour, let's say that we have a concentration here of 25 milligrams in 4 milliliters of medication, that would mean that the minimum dosage here, we're going to use our dimensional analysis. Any rate can be used as an equivalency. That 5 milliliters is equivalent to 1 minute of infusion. Well, our 5 milliliters per 1 minute, we can also use that 25 milligrams is equivalent to 4 milliliters of fluid. We're going to do times here. We'll put in a conversion factor. We need to get rid of milliliters. We'll put that on bottom. That'd be 4 milliliters to 25 milligrams. The milliliters cancel out. 5 times 25 is 125 milligrams. On bottom, 1 minute times 4 is 4 minutes. If we divide that out, that's a 31.25 milligrams per minute is the minimum dose. That's the slowest that medication can be infused into the patient. Well, if our patient needs a smaller dose than that, that is looking at somewhere around a little over 1,800 milligrams an hour. Let's say our patient we only want our patient to get 1,000 milligrams per hour, which would be 1,000 divided by 60, 16.67 milligrams per minute. About half of what that is capable of, we have to dilute that solution. So these dilutions, these change of concentration or concentration adjustment formulas are vital for helping us dilute that solution, because the label is telling us from the manufacturer or from our supplier, there are 25 milligrams in for every 4 milliliters of fluid. We need to be able to dilute that exactly, precisely, so that we can reduce the flow into the patient if necessary, but it has to be done accurately so that we still know exactly how much medication that patient is getting. That dilution ratio then, let's say we do a 1:3 dilution. Well, the minimum infusion rate before was 31.25 milligrams per minute. Come on. In fact, I don't even have to write it out as a rate like that. I can write it out as a unit rate per minute times that 1:3 dilution. 31.25 times 1:3 gives us a 10.417 basically milligrams per minute is our new minimum infusion rate. Well, that is well below the desired 16.67 milligrams per minute that we want for this patient. So that dilution is the tool that allows us to adjust our medication. Okay, that is enough for this week. Some homework for you. In your book, page 134, 1 through 11, just do the odds there. That's only 6 problems. That is on that formula, that ratio of concentrations being equal to our dilution. And then we have page 138. 1 through 17, the odds there. That's only 9 problems. That is using this change of concentration or concentration adjustment formula. With that, you guys have a great weekend. By the way, I did get tests from Clear Lake. I haven't had time to grade them yet. I'm still waiting on Mauston. So if you guys want to double check with your person and see if they've been sent out, I won't have any time to grade them this weekend anyway, so I won't get to them until Monday. But just something to check on. So anyway, you guys have a great weekend, and we'll see you on Monday. Whoops, if you're trying to talk, somebody's trying to talk there. I see it, it's muted.